Every single second, a popular web server faces thousands of overlapping HTTP requests colliding with each other all at once. To keep the server from crashing or cross-contaminating user information, the system has to perfectly isolate every single piece of incoming data. This is the HTTP context. It is a standardized, completely isolated data container created the exact millisecond a request hits the Kestrel web server. In this animated diagram, you can see the HTTP context splitting into 3 distinct data streams: the incoming request carrying the URL and body, the outgoing response managing status codes, and the user identity claims holding authentication details. By capturing all of this in one place, the HTTP context acts as the single source of truth for an individual request's lifecycle. It solves the concurrency data isolation problem. However, a container is just static data. It cannot process itself. It requires a powerful engine to move that data forward. Look at this exact C# signature for the request delegate. This is that engine. It accepts the HTTP context, performs an operation upon it, and then returns an asynchronous task. That return type ensures the server thread remains unblocked and ready to handle other traffic. The request delegate operates as the atomic unit of action that actually drives the web server's processing capabilities. When you pair an HTTP context with a request delegate, you create a single piece of middleware. This diagram illustrates a single middleware node in action. It receives the HTTP context packet, inspects or modifies the data inside, and then makes a crucial decision: whether to invoke the next request delegate in the sequence. Zooming out on this sequence, we see how these individual nodes form what developers call the onion architecture. It's a nested series of concentric layers with a pathway moving inward to a core and then bouncing back outward. The architectural power here lies in its bidirectionality. Components process the incoming request on the way in and then process the outgoing response on the way out. Let's trace a data packet passing inward, starting with a logging gateway. It leaves a timestamp record behind. Moving to the static files gateway, the middleware checks for an asset, comes up negative, and continues inward trajectory. Next, it reaches an auth gateway. The system validates the identity data, gives a green checkmark, and passes it through. Finally, hitting the central endpoint core, the web page is generated and written. The packet transforms color, ready to move backward. The newly completed response now travels outward, flowing back through the auth, static files, and logging gateways in the exact reverse order. This systematic traversal guarantees that every single request and response is handled uniformly by the server's architectural layers. Because the pipeline follows this strict sequential logic, the order in which you register middleware dictates your application's stability and security. Placing authorization before authentication creates a catastrophic ordering failure, like a locked door demanding access levels before the user presents an ID. Conversely, placing the exception handler first expands a protective umbrella, catching errors from deeper layers. This precise sequence also allows for short-circuiting. Terminal middleware can reject invalid requests early in the chain, saving the server from wasting processing resources. A data packet hits an auth node and fails validation. The middleware simply chooses not to call the next request delegate, immediately bouncing the packet back out as a red 401 unauthorized response, without ever reaching the central core. ASP.NET Core operates entirely as an orchestrated chain of request delegates handing off an HTTP context. It gives developers total, efficient control over global web traffic.